Hello, good afternoon, everyone. Today I'll be talking about seasonality and suppression of turbulence in the northern Bay of Bengal at 18° north as measured by kypods. I am Ritabrata, a graduate student with Professor Rama Govindarajan here at ICTS. And this project was done in collaboration with Emily Shroyer, Thomas Farrar, Robert Weller, James Woom. And thanks to the funding agencies, Ministry of Earth Sciences in India, Office of Naval Research, funding through IISc, TFR Hyderabad, ICTS, UDSOL, Oceanographic Institution, Oregon State University, and thanks to the organizers. So today I'll be talking about the mooring that was deployed at the Northern Bay. It was an OMM UDSOL mooring. It was deployed on around 29th of December, around 8th of December 2014, recovered on 29th of January 2016. This is the location of the UDSOL mooring, and it had many sensors on it, and we are looking at the turbulence measuring sensors called kypods. These were distributed from 20 meters to 65 meters. We lost one and another wasn't good, so we'll just talk about these four sensors from this location. In an hour from now, probably Deepak would be talking about turbulence from some of the other sensors here in the bay, in the southern bay. Why it's interesting, mostly probably everyone knows, but it receives a lot of fresh water, and shown by lots of groups, and very recently by Sri Lekha and Jared Buckley et al. They show that the eddy and the Ekman flow is very important in taking this freshwater discharge from the lots of rivers in the northern mouth of the Bay of Bengal into the Central Ocean. But we haven't yet looked at how this freshwater modulates the dipycnal mixing, and that's what we are going to do with our measurements from the kypods. Very brief overview. I would refer to this paper for kypods, but it measures speed and temperature fluctuations with two thermistors, and then with some approximations, which I'll be happy to talk about later, we arrive at the value at a quantity called chi, which is the rate of destruction of temperature variance, and this simple formula relates it the chi to the turbulent diffusivity. So from now onwards, when I say turbulence or turbulence, it might mean turbulent diffusivity or the other way. And this has this Tg. This is the mean vertical temperature gradient. Just to give you just an idea of what the vertical scale is. If this 22-meter kypod, we had a SB 37 at 19 meters and another at 23 meters. So we are quite happy with that. A very brief summary of the deployment during the transition to the southeast monsoon. This is the climatological mean. The temperatures, upper 26 meter temperature increased. And then when the monsoon winds started and precipitation, there was a drop in the upper 20 meters temperature, reducing the stratification in temperature. Then again, in the later half of the summer monsoon, temperature stratification started. And one of the most amazing feature of this is shown in the salinity, where you see all these drops in salinity are the arrival of the freshwater at the mooring location. And these are the black and the cyan lines are the temperature and density based MLDs. After the arrival of the freshwater, the density based MLD always remains shallower than the temperature based mixed layer depth. And the difference between the two is called in literature as the barrier layer. So this is the summary of the seasonality in turbulence as measured by the kypods. The first panel shows the wind stress distribution. The wind stress, and the panel on the right shows the wind stress distribution. We have selected two periods in the summer monsoon. The first one is black and the second one is shaded red, and this shows the distribution in this two periods, black corresponding to black, red corresponding to red here. And as it's summer monsoon, it's of course higher than the distribution in the whole year, which is in the black solid outline. And the panels 1, 2, 3, 4, 5 are the kypods at different depths. One very appealing feature of this is that the 22-meter turbulence seems to follow the wind stress. where it goes above 10 raised to power minus 2 in the later half of June. And one other thing I would like to point out is when we go downwards in depth, the median values in the turbulence diffusivity tend to separate out, by which I mean at 65 meters in the second half of the summer monsoon, the median value of diffusivity was minus 0.5, whereas it was about minus 3.8 in the first half of the summer monsoon, which was of course not the case as you can see from this distribution at 22 meters. And this marks the way we have divided is that this marks the arrival of the low salinity water in the mooring location, and I'll talk about it later. Very crude correlation. By mathematical terms, you probably wouldn't say this is a very strong correlation, but depending on being lenient because of the noise involved, I would say this is a stronger correlation than this. Again, so this is a 22 meters, this is a 46 meter. This is sometimes inside the mixed layer, sometimes at the base of the mixed layer. This is always below the mixed layer in the Bay of Bengal. So even during the southwest monsoon, this shows a stronger correlation as compared to the 46 meter turbulence. And this is about a 1.5 month period where the first one shows the wind stress, and this hump you see is the cyclone Komen, and cyclone Komen brought in with it some fresh pools of water, mostly of course like a river and discharge and precipitation, and it came as distinct pools into the mooring location. And the red line denotes the 22 meter turbulence, the black denotes the 65 meter turbulence. The 22 meter followed the surface winds. As the winds relaxed, the 22 meter diffusivity died down, but during the existence of this low salinity water, it could not come back to the original value that we started with in this panel. This shows the relative contribution of temperature and salinity to density. These big peaks that you see are the averaged DSDZ over the upper 25 meters. And I'd like to point out that during this period in the around 10th of July, coincident with increase in salinity stratification, I'm pointing towards these humps. Salinity stratification, we also have a temperature stratification here, and both acted towards reducing this diffusivity at 65 meters, which is below the mixed layer. We also observe the periodicity in turbulence. One of the interesting cases is a diurnal signal at 65 meters depth, which is not narrowband at 22 meters. And a thing to note is that this existed even when there was a cyclone of about 85 kilometers per hour speed at the mooring location. So this is a topic of interest, and we exactly don't know what is the reason behind this existence of this diurnal cycle in diffusivity, but it might be biological in origin, given that mooring can attract zooplanktons of fish, but we are really worried about why it's 30 days long, but we'll look into it. And another feature that captures the seasonality in turbulence in the northern bay is the suppression of turbulence. The first two panels are weekly average wind stress and salinity, and this big bar that you see is the cyclone Komen, and the last panel shows you the turbulent diffusivity averaged average below the mixed layer from 46 to 65 meters, and this color plot is showing you how the 65 meter doesn't even respond to this cyclone. So this small blip that you see is just due to the response at the 46 meter and a slight response at 55, but due to this increase in near surface stratification denoted by this n square, there was a big suppression of turbulence at this location. So we think that the enhanced near surface stratification due to the arrival of very low salinity water at the mooring location at the end of July, which was also which was also helped by the cyclone with high wind stress periods. It led to this suppression of turbulence below the mixed layer by shutting off the communication of vertical forcing agents. So rather than giving you some qualitative statements, I have some quantities to tell you in the conclusions. So during the southwest monsoon, during the transition to the southwest monsoon, the median diffusivity was 10 raised to the minus 5, increased to 10 raised to the minus 4, and the highest diffusivity was 10 raised to minus 2 when the wind stress was in excess of 0.3 Newton per meter square in daily averages. And the prolonged shutdown of vertical mixing below 45 meters after the arrival of this low salinity water and when the low salinity water existed over the northern bay. During this shutdown, daily median and mean values of diffusivity remained in the range of 10 raised to the minus 5 and 10 raised to the minus 6. Minus 6 is the molecular value. So if it didn't make sense, in very short, turbulence in the northern Bay of Bengal has a seasonality, shows intermittent behavior. Turbulence below the mixed layer shut down after the southwest monsoon. And I just put up a last slide after Professor Sarkar's talk, last talk, that we were looking at the measurements or the turbulence measurements from kypods at a point when freshwater filament arrived at the mooring location. I don't know what I can say much, but some of the enhanced turbulence at the base of the freshwater current that arrives. It has an inertial signature to it, and these colors denote the epsilon values. So this is something we are looking at, and it will be helpful to have your feedback. Thank you.
Any questions? Yeah.
So as you can see here, these are fixed point measurements, but the good thing is we have the time series. We have 1 year data. We don't have profiles, but we have 1 year data. What is the secondary peak? Yeah, I mean, if you are thinking about looking at a profile, I wouldn't know if that peak sustains along the depth. I mean, if there might be a peak at some point, I don't know if it has a slope somewhere. I can't say if it might be high, but I don't know if it has a slope to call it a peak. I don't know if I'm making it clear. Yeah. I mean, I have, if I have measurements somewhere here, I can't say if it was like this or like this to call it a peak. So, yeah.
Yes, we can continue later.
Okay, yeah. Yeah, these are fixed point sensors.
Let's thank the speaker again.